Hey guys, welcome to Digital Srini channel on YouTube, and if you haven't already done so, please go ahead and hit the subscribe button because I know you're going to love the content I have and the content that I know I'll be putting on this channel in future. Okay, now let's get to the topic of this video. In fact, it's the topic of this one and the next video. In these two videos, we are going to learn about how we can pre-train a unit using autoencoders. What do I mean by that? Well, when you define unit or when you define any neural network, you're going to initialize the weights, right? The whole point of training a neural network is learning the weights and biases using your backpropagation. You're updating the weights, checking the result, updating the weights, checking the result until you're happy with the metric that you're tracking. Okay, now when you're updating these weights, you hope that it's heading in the right direction. Hopefully it will if you pick your loss function and your optimizers the right way. But typically the weights are assigned in a random way. Okay, you can use transfer learning, and where transfer learning helps is you already know that there is a model that has been trained on millions of images. So let's go ahead and start with those weights, meaning they probably already know how to detect certain edges or rounded features and so on, and then you go from there. So what I'm proposing here is very similar to that, except instead of using pre-trained weights from ImageNet and VGG or something, I'm talking about using your own autoencoder on your own data and then generating weights. Okay, so what do I mean by that? Now you have let's say hundreds of electron microscopy images or some images, right? And you know that in future you'll be keep working on these, and then you're trying to train a model. It makes sense for you to put some time ahead of time in generating the initial weights. Instead of starting with random weights, start with weights where it has been trained on your own data. This is exactly what we are talking about. Now, how do you generate these weights if you don't have the labels, right? I mean, in UNet, you have your images and you have your masks, and you're training on it. Well, that is exactly where autoencoders come into picture. What is an autoencoder? It learns how to reconstruct your image based on your input image. It learns how to reconstruct your input image. In this example, you can see how you have a reconstructed image. This is an actual reconstructed image and not the same image. Okay, so you train this network where it goes from a larger size to a incrementally smaller, if that's a word, incrementally smaller, representation of your image, and then you're decoding it back to original. In this process, when you're doing this, we are updating the weights of all of these, and I'm proposing do that, and take the weights from your encoder and use them as part of your unit, because unit is nothing but an encoder decoder network, just like autoencoder. So let's get into the next level so we can understand this, and then we'll get into code in a minute. Okay, so I just explained that this is your encoder, right, in an autoencoder network. Now what happens, like when you send an image through, it trains this network. It may take I don't know how many ever epochs, and then at some point you're like, okay, let me send you an input image, and then it reconstructs that input image back, right? So this is the definition of autoencoder. During the training process, it learns different features at different depths, and it learns the edges or the basic, you see how there are certain edges going on right there in Mona Lisa, and in some images you can see that. And as you go deeper and deeper, it's actually learning higher and higher features. In fact, the outer layer features may look the same between random initialized weights and pre-trained weights, but as you go deeper and deeper, this is where you actually see some difference, because this is where it's feature rich now. Okay, at outer layers, it has a very much knowledge of pixel awareness, let's say. As you go deeper and deeper, it's more feature rich. Okay, so that's why it's if we can pre-train this and take these weights and use it as part of unit, that would be amazing. So let me just show you a few of these similarities. First of all, let's start with similarity between autoencoder and a unit, right? So if you look at autoencoder, again, this is the third time we are seeing in this part of presentation. This first part is encoder, because we are encoding a larger size image into a smaller size, and then we are decoding. This part is the decoder. So if you look at a unit, hopefully you watched the last 30 videos or so where we have been talking about unit. So if you look at unit, this is exactly the same, except you bend it into a U shape. So you have a encoder right there, right? This is nothing but this. Yeah, I just arranged it in such a way that it can form a U using this. That's it. And you have a decoder. So it's exactly this and that. Why is it called a unit? Because in addition to this, in addition to an actual autoencoder, we have skip connections, meaning the information from this layer is going to that layer, information from here is going to this layer. Why? Remember, the earlier layers right here, they have information about pixels. As you go deeper, you have information about features, more information about features. A combination of this gives you semantic segmentation, pixel awareness plus the feature. Yeah, so that's what a unit is. This is exactly why I'm proposing to take, if you have a million images that are completely unlabeled, if you have labeled data, that's fine. Go ahead and train a unit, and then you're okay. You don't need to spend this. But then if you have 1 million unlabeled images, how can you benefit from them by not labeling every image? So just dump all those million images, train an autoencoder, and then just get the encoder part and use it as part of your unit. This is exactly what I'm proposing right here, okay? So again, information as you go deeper and deeper gets more feature rich. So let's just compare that with a few features. By the way, when we jump into the code, I'm going to show you a quick autoencoder and then how to print out these features at various depths of your network. Okay, so we'll get there in a second. So here is the feature output at layer number, the first layer. Okay, after the first layer. This is not the input, but after the first one, convolutional layer. This is how your input looks. The features look like. Okay, so as you can see, you can still see Mona Lisa right there. So it's still trying to learn, even though these are random weights. But if you use a pre-trained network, this is how the weights would look like. It may not look that different, but again, if you try to squint your eyes, you can see the difference. Where in this case, where you have pre-trained weights, some of the features are right there. Some of the features, you see the hotspots right there. Yeah, you see hotspots. Wherever you see hotspots, that means it's learning something right there. Yeah, so that's the feature response right there. So there you go. And then let's go to layer number 8. Now you start to see the difference between random weights. Random weights still look pretty much the same as before, right? As the layer number 1. Let's go back. This is layer number 0. These are all random weights. This is pre-trained weights. This is layer 8. Looks very similar to layer 0. Because these are random weights and this is pre-trained. Now you see much more definition of the structure. Now let's go to layer 16. Again, these are random weights at layer 16, okay? And this is pre-trained weights. You already have a lot of rich information. And finally, let's look at, let's look at a couple more. Layer 24, again, random weights, everything random. And here you start to see some structure. They look a bit more blurry because we are going smaller in size. And I'm expanding that. That's the only reason they look very blurry compared to initial. So as you go deeper, feature rich, but not necessarily spatial rich. Okay, so there you go. So and finally 32 layer. It's not like you don't even you see anything here. You don't even see Mona Lisa anymore because these are all random weights again and again. With pre-trained weights, you have hotspots showing something important, something useful for segmentation, for reconstruction right there. Okay, so this is the thing that I wanted to convey in this video, like remind you what an autoencoder is and how to extract features. Now let's jump into the code to repeat this. Okay, so let's start by understanding single image reconstruction in this video, just like what I've shown you in the presentation part, and then look at some of the features. I'll share the code so you can do this yourself. This is a very educational thing to do if you want to get into autoencoders or even any deep learning. This really helps you understand the features, right, at various layers. Okay, so where do we start? First, let's go ahead and import the required libraries: matplotlib, numpy, opencv. Let's go ahead and do that. This is actually, first let's make sure we are in the right working directory. So again, I'm using Python 3.7 and TensorFlow 2.4. So let's look at my present working directory. That's definitely not where I want to be. I can navigate through here, or I'll just type some mistake right there, and it says, hey, this is not good code, or this is a mistake. So let's, now if I do my directory, it changes, because the settings, the way I have settings in my Spider, anytime I run a file, it just automatically changes the working directory to that. So this is the easiest way. Anyway, little tricks. Now let's run these lines of code, and let's also from Keras, I'm going to, what did I do? TensorFlow.python.keras. Sorry, I am not supposed to edit the code while I'm doing a video, because I have no clue how that's going to work out. Normally I just do from Keras .preprocessing, import this, from Keras.layers, import this, but since I switched to Python 2 point something, sorry, TensorFlow 2 point, I started to do TensorFlow.keras. Okay, just my personal preference. Otherwise I used to directly import Keras previously. Just a habit. Okay, so there you go. So again, I don't think we need these, but this is something that I usually import if I'm trying to build a deep learning model. Okay, we'll go through these step by step in a second. This is pretty straightforward. I want to resize my image to 256, so I just defined it here, and my image data, which I'm going to capture. Am I going to capture image data? I think, yeah, right there, image data, empty list, because I want to append my image into array. This can be useful if you have multiple images, right? So anyway, let's go ahead and define this, and I'm going to read my Mona Lisa image right there as color, yeah, all channels, and convert my color from BGR to RGB. That's not a necessary step, but I do that usually if I want to visualize things. So that makes it easy for us to intuitively understand what's going on. Okay, now I'm going to resize my image. I think this is probably 256 to begin with, but that's okay. I mean, why am I resizing? Because my network expects 256. That's pretty much it. Okay, now let's go ahead and image data.append. And finally, reshape this array. Why am I doing all of this? Because for the network, I want my input to be in the shape of n, x, y, and number of channels, right? N is number of images, x, y, image dimensions, and number of channels. This is obviously, you probably know that. Anyway, let's go ahead and divide the pixels by 255. So it's a way of scaling. So now I'm all ready. My image array is float 32. So up to this point, I should probably have skipped through this and just said, I'm loading an image. That's it, right? But again, my viewers come with various backgrounds, so this hopefully can help. Okay, so now comes to the autoencoder part. So what is the plan? Now we have an image. We need to encode and we need to decode this image. So I built a model. I mean, I have a file called models where I have a function to build autoencoder. Let's go through that now. Okay, so I'll share this again with you. This one, what I have defined is a convolutional block, a function that builds a convolutional block that has two convolutional layers, and of course activation for each of these layers and batch normalization. So this is a convolutional block. And then I have an encoder block. What an encoder block is basically a convolution block plus a pooling layer. That's it. This is again nothing new. Unit, we have built a unit this way. Okay, so a unit is basically a convolution block plus max pooling, right? So, and then you keep going and then you do the decoder block. Okay, so far I hope makes sense. This is my encoder block, a block of an, to build my encoder. The decoder block is exactly opposite. Instead of convolution, I have transpose convolution. Yeah, to go the other way. Think of this as upscaling. I have made a video on this topic. Difference between upscaling and conv2d transpose. Please watch that video if you don't know what the difference is between these two. But either way, in the decoder part, we are going to use, along the decoder path, we are going to use conv2d and the convolutional block. Okay, this is again our decoder side. So let's go ahead and build our encoder. Build our encoder, yeah, going from a large image to the smaller. How do you do that? My encoder block, right there, we have my encoder block. I'm repeating that 4 times. It's up to you how deep you want to build. The reason I built it this way is I would like to use exactly the same encoder when I build my unit later on. When I build my unit, I would use exactly the same structure. This is why I can use the weights from there to here. Okay, that's the whole goal here. Okay, so I'm going to build my encoder using 4 of these, and progressively I'm increasing the number of filters from 64 to 128 to 56, 512, and 1024. And progressively your image gets smaller as you go. Why does your image get smaller? Because in our convolutional block you have 3x3 kernel that kind of brings your image smaller and smaller as you go through these layers. I hope you know the basics of that, right? So that's building the encoder. And what does the encoder give out as outputs? We are actually getting 2 things as outputs. For autoencoder, we are not going to use both. We are just going to use one output. But what is my encoder block giving out? It's actually giving out the output of convolution block and also the output after the pooling. That's it. The whole point of encoder block is to make sure we get 2 outputs. One is an output of just the convolution block and the output after max pooling. Why? Because in unit, remember the skip connection part? The X, the output of convolution block, is what's being added to the next level in the decoder. Okay? Again, these, I assume you know these basics. Otherwise, this video can be one of the most confusing videos that you have ever watched on my channel. So far, we are trying to build an autoencoder, and you may be thinking, why are you complicating things? Autoencoder is easy. Just put like 10 lines of model.add, model.add. Yes, you will be right. But the whole point of this video is to show how the same encoder that I'm going to build is going to be used also in unit. So once we train this encoder and get the weights, those weights can be transferred to the unit. Okay, that's our goal. So now you know how to build encoder. Just these 5 blocks, and then my decoder goes from this point and then symmetrically goes the other way, right? So 1024 and then 512, 256, 128, and 64. That's exactly what I'm doing right there, going the other way. And then finally it gives me a decoded image of whatever the input is with 3-channel output, 256 by 256 by 3, right? So that's exactly what we are doing. And anything, I think that should be it. And when we build an autoencoder, it's basically encoder plus decoder. That's it, right? That's our autoencoder. That's exactly what I'm doing. My input is going to be my input image with a shape of that, and my autoencoder model is basically my input, and then this is my output, right? How do you define a model? Your input and output. Input is my input image. What is your output? Your output is basically that, a decoded image. And how do I define that here? Which is nothing but build decoder. And the input to the decoder is my encoded image, which is basically that. I hope this makes sense. Again, some people may think this is too basic. Some of you may think, hey, what are you talking about? But watch this video a couple of times, practice this, and things will make sense. This is a great way of learning about these neural networks. Okay, so much about discussing the model. Let's just go ahead and import our build autoencoder, the function that we just defined that builds the autoencoder. What does the build autoencoder need? It requires the shape of my image. And what is the shape? 256 by 256 by 3. So let's go ahead and build this autoencoder. So it's building it right now. Basically, when I say build autoencoder, it's putting together this model with input image size as input image as the input, and then the decoded as the output. That's exactly what it did. Now let's go ahead and compile the model. How do you compile an autoencoder? Well, let's use an optimizer called Adam. This works in most scenarios. And for loss, let's use mean squared error. Why? This is not a regression problem. Why are we using mean squared error? Well, in a way, this is a regression problem because we are trying to minimize the error between the output and the input images. Right? We're trying to minimize this reconstruction error between the output and input. And if there is no error, I get the same output as the same input. That's why I'm using mean squared error, and we can track the metric's accuracy. So let's go ahead and build that. And now let's print the model summary. This is basically my encoder decoder network. So I start with 256 to 56.3 and then increase the number of filters to 64. As you know, we did that, 64 to 128, 128 to 256. So the filters increase, the size goes down by half each time. Yeah, the filters go up by 2 times. Okay, I think 16 to 1024 is the last one, and then it goes up symmetrically. 32, 512, 64, 64, and finally we'll end up with 256 to 56.3 image. And there are about 28 million parameters that need to be trained, but don't worry, this is just single image, so it's going to be super fast when we train it because there's not much data, even though there are 28 million parameters that need to be adjusted. But I really want to make sure you understand this, what we are trying to do. And let's go ahead and model.fit. My input is image array, my output is image array. Normally you give X and Y. In my case, X equals to Y because this is an autoencoder. We are encoding, decoding, okay? And let's run this for 500 epochs. And while it's running, it should be pretty fast actually, especially if you have a GPU. Yeah, there you go. It should be done in a minute or so, but just want to confirm one final time. But I just want to reinforce this message one final time. What we're doing is an autoencoder where we did build an encoder that goes from some size to smaller size incrementally because we have this max pooling, these and max pooling operations right there, the convolution and max pooling operations. And then the number of filters are going up incrementally. Exactly opposite is happening in decoder. So as you can imagine, when I get down to UNet, I'm using the same encoder, but then a different decoder. Yeah, if you just use the same decoder, then it's an autoencoder decoder because decoder block for unit needs the skip features, and we already know where the skip features are coming from. These are the skip features that we get from here. Where is it? Yeah. So these are the features. Okay, there you go. The training is done. So let's go ahead and reconstruct, like predict on the on my original image. So hopefully it should reconstruct a decent image. So let's go ahead and print out the original and the reconstructed image. That's not a good reconstruction. So what kind of accuracy? 93, right? So let's do this one more time. And I'll pause the video. So I won't waste your time. And I'll pause the video and then let's see how dramatically it comes. I remember if I did this like 1000 epochs or something, then the accuracy was super amazing. Okay, so let me pause this and then continue within literally a few seconds. And yeah, a few seconds later, now we had about 93% accuracy. Now this is about 96%, and let's see if it made any difference. So what do we need to do? Let's go ahead and predict this one more time using the new model, and let's print this again. Oh, there you go. Right, so this is with 500 epochs. This is how the reconstruction is, and extra 500 epochs, this is where we got almost identical. I mean, I can see some difference in color. This is 3-channel image, right? But then look how good this is. This is a bit blurred compared to this one, but amazing. But our goal is not to reconstruct the best image. Our goal is to make sure we reconstruct it as good as possible, but then take the weights from the encoder. So just to show you that part, not how to take the weights, I'll save that for the next video because I don't want to make this a 1 hour long video. So let's look at the features. How do you look at the features from your model? So first of all, let's build another model, another autoencoder. So this is basically, remember here, we built a autoencoder right there, and then we compiled, and then we trained. Now I just want an autoencoder that hasn't been trained, meaning with random weights. Why am I doing this? Just so we can look at features before and after. That's it. No other reason. And then I'll make my model, the current model I want to use as model 2, which we just defined. And we are going to get our outputs as layer.output for each layer in my model, starting with first one. Yeah, the 0th one is the input, and then go ahead after the first one. So this line, when I run it, you will see that my outputs right there has 63, size of 63. It's a list of 63 Keras tensors. Okay, these are the 63 layers I have in my autoencoder. Okay, now let's define a model for visualization, which is basically my inputs is nothing but the inputs coming from this model, which is the input or input image, and my outputs is just the outputs that I just defined here. Which means if you do this, you'll get 63 different outputs, each one corresponding to each layer here, which gives us everything we need for plotting. So let's go ahead and define this model. And we just defined the model. We need to predict using that model. Remember, we haven't trained on this one, right? So let's define my input image is basically my image array, which we just did earlier, right? I mean, that's what we called it. Yeah, the Mona Lisa image. And let's generate our feature maps. Feature maps is basically this new model we defined, .predict on my image. And when we do that, we should get 63 outputs, hopefully, feature image, feature maps, 63 NumPy arrays. Why 63? Again, we have 63 layers. That's why we defined our output equal to outputs. We get 63 layers. And now I have 63 feature maps. Just pick which one you want to plot. That's exactly what the bottom part does. So let's look at just single layer. I'll share the code. You can experiment with this. Let's look at the last layer, 32nd layer. Well, 63rd layer is the last layer, but 32nd layer is the last layer of autoencoder, exactly halfway through. Okay, so let's look at the layer number 32, and let's plot my original image and the feature map. Okay, right. Actually, I'm not plotting original image and feature map. Sorry. Let's plot each feature maps as a grid of 8 by 8. So we'll get 64 feature maps. Okay, for the layer number 32. So let's go ahead and plot it. And right now it's predicting. Sorry, it's plotting each one of these, and there you go. I already showed you this as part of the presentation. I just want to make sure you see it live. And this is based on random weights. Now let's use the trained weights. How does the the feature maps, how do they look like? So let's go ahead and run all of these lines and then finally plot them once we have it. Go ahead and plot it, and hopefully we should see some structure. There you go. Nice structures right there. Okay, so I hope you got the point of using or the benefits of pre-trained models. Now you can use, for example, the ImageNet weights. That definitely helps. This is what we call transfer learning. But ImageNet is a bunch of animals and trucks and these type of things, right? If you really want to work on a bunch of electron microscopy images, where you want to detect mitochondria, or whether you're in material science, or whether if you want to perform semantic segmentation on satellite images, it does make sense to collect as many satellite images as possible, train an autoencoder, get the weights, and use those weights as starting point for transfer learning, and then do semantic segmentation. This is exactly what we're going to do in the next tutorial. Now that you understand what autoencoder is, in the next tutorial, we're going to train an autoencoder, save the weights on a bunch of images, not just one image, a whole bunch of images, save the weights, and use those weights to train a unit. Okay, so please stay tuned for the next video. Hopefully you'll find it useful. Okay, thank you guys. Don't forget to subscribe.